Section 5.3 takes into account a specific type of circular motion that you experience on a very regular basis. It's turning on a road, and we're going to talk about banked and unbanked curves. So when you turn on a road, it creates a sensation that you're getting pushed outward. Imagine that you're in a car and you're in the driver's seat and you turn toward the left. When you do, your body feels pushed against the right side of the car. But that's not some sort of a force pushing you on the outside. That's really your own inertia. Because remember, if you're in this car and you're making the turn, your velocity is tangential. Right? You want to continue experiencing a velocity out that way. However, when you turn the car's wheels turn and they create a force toward the center of the circle. And that net force, which is caused by friction in this case, is causing you to turn. And so that means that you feel the sensation of being forced inward, and that's what's really going on there, is the force from the car is acting on you. And since the force from the car comes from friction between the tires and the pavement, that means that you're actually getting a sum of every single force of friction from every single wheel, creating that net force, which is a force of friction. So one of the things that we would look at is for your car, you're going to be experiencing mg and Fn. And then if you're making a left-hand turn, right, there's you, and you're making a left-hand turn, then that means that the individual frictions from each of those would create a force of friction here. And so in the y direction, you'd have Fn minus mg equals 0. But in the x direction, you'd only have friction. There's no other force acting in the x direction. So that force of friction, which is a static friction for tires, is equal to mass times acceleration. So since the acceleration is causing you to turn, that's centripetal acceleration. So the force of friction is going to be equal to mv squared over r, your centripetal force from your centripetal acceleration. Friction is the force that caused it under this circumstance. So that means that using the y equation, you could solve for the normal force and add in the coefficient, and you could solve for any component of that particular force. So we're going to take a look at a few examples of how to apply this particular phenomena. All right. If the wheels of the tires are rolling normally, and that means that there's no slipping because you know you don't want your wheels to skid if you're driving, then the friction that's being caused by those tires is static friction. If the static friction isn't big enough, the tires are going to slip and you're going to drive off because you're going to lose your net force. That means that we can determine, like we do in example 5.6, whether or not a certain car can make a certain turn at a certain velocity. So we're going to be looking at a car with a mass of 1,000 kilograms making a turn of radius 50 meters with a velocity of 50 kilometers per hour, which we can convert to 14 meters per second. And we're going to determine if this car can make the turn on a dry road, where the coefficient of static friction is 0.60 newtons, and on an icy road, where the coefficient of static friction is 0.25. So on a dry road, all right, we know that for that car, if it's an unbanked curve, the normal force and gravity give you a net acceleration of 0. So the normal force equals mg. And in the x direction, the only force acting is static friction, which is equal to ma. Since it's supposed to be making us go in a circle, that means our static friction, ms Fn, is equal to mv squared over r. So the force that we experience for going at 14 meters per second, the force that we experience from going there is 0.60 times 1,000 kilograms times 9.8 meters per second squared, which gives us a force of 5,900 newtons. Well, now we need to know, is that going to be enough to allow us to travel that circle? Well, that circle is going to be a mass of 1,000 kilograms times a velocity of 14 meters per second squared divided by a radius of 50 meters. And if I solve for that, I get that we need a force of 3,900 newtons. So it's safe on a dry road, because 5,900 newtons, the maximum static force that can be provided by tires with a coefficient of 0.60, is greater than 3,900 newtons. So we're okay on dry. On wet, however, you have a maximum coefficient of 0.25 times 1,000 kilograms times 9.8 meters per second squared, which gives us a force of 2,500 newtons. And we know that traveling at 14 meters per second on a 50 millimeter radius curve for a car of 1,000 kilograms is 3,900, and the maximum friction that can be allowed from that car is 2,500. So 2,500 newtons is actually less than 3,900 newtons. So it's unsafe on icy. Or another way of saying that is that the car will skid because you will exceed the maximum static coefficient of friction in order to make that curve. So why is that so dangerous? Let's think about this. All right, when you're going in a curve, you know, imagine this curve and imagine this car and imagine your tangential velocity v. All right, when you turn your wheels, all right, what you're doing is you're changing the direction of your friction. All right, if you're driving straight and your wheels are pointed straight, then then the force of static friction is in the same direction as, or on the same axis as your travel. However, when you turn the wheels, right, if the wheels turn, then your friction is also going to turn, and so your force of static friction is pointed perpendicular, and that's what allows you to turn the wheels, change the direction of the static friction. However, if you exceed this maximum amount that can be provided by static friction, then you're going to get kinetic friction, and kinetic friction resists motion. Well, what direction is your motion? Your tangential velocity is straight, not along the path of the curve. So when you skid, suddenly your force of friction is going to be in a completely different direction than it was initially, which means that you have absolutely zero net force in the direction of the circle. So you will no longer travel along that circle, and maybe you'll reduce your speed a little bit, but your tangential velocity will be in a straight line. You will slid or skid off of the road in that particular situation. So it's actually incredibly dangerous to exceed the maximum force that you can receive from static friction. And it's even worse if your tires stop rotating, because when the brakes are applied too hard and the tires stop rotating, then that means that there's only going to be skidding. That skidding can only resist your tangential velocity, and as a result you will have absolutely no force toward the center of the circle. Anti-lock brakes are actually designed to limit the brake pressure just before the point where the sliding would occur, the wheels would lock, and that means that the car will allow or force the wheels to continue to roll. It means you're going to have less braking, but it's a much safer scenario in the event of a turn. So how do we reduce the fact that we rely so much on friction to make turns? The way that we do it is we bank a road, or we set a road so that it's at an angle. And when we do this, right, what happens is that the normal force, all right, for this car actually acts at an angle so that it continues to be perpendicular to that road, whereas your gravity continues to be straight down. This allows us to travel in a circle with less friction. And why is that? Well, let's take a look. If we assume that we want our net force to be pointed toward the center of the circle, then what we want to do is we want to say that, hey, this is the direction that we would like our net force to be in, or our centripetal force, because we want to make this turn. Well, that makes sense. So what we would do for this particular situation is we wouldn't tilt our axis. We'd make our axis so that mg pointed straight down, and here the normal force is acting at an angle, all right, by similar triangles, it's this angle to the y-axis. And now here you can see that if I break this down into components, then what I am going to end up getting here is I'm going to end up getting a component of the normal force in the y direction and a component of the normal force in the x direction, and that x direction is the direction of our centripetal force. So now you have normal force acting toward the center of the circle. This situation reduces our reliance on friction. So that means that we can actually travel at a higher speed before we're applying so much force that the car will skid out of the road. So if we have a curve at angle theta, then what we end up getting is that that angle, which ends up being this angle, will give us an x component of our normal force. So our force normal in the y direction would be f in cosine theta, and for our force of normal in the x direction we get f in sine theta. And so that sine theta, if we set it at a speed so that this normal force is the only thing that we need to make the turn, then we know that the net force in x direction would equal f in sine theta, which would give us our centripetal motion, or mv squared over r. So this situation where you need absolutely no friction to stay in the curve, all right, this velocity right here is called the design speed of a banked curve, which is great because the design speed for a banked curve is a speed at which you're not going to need to or depend on friction. This is really great for especially dangerous roads or roads that get icy and have lower amounts of friction that can be offered between the tires and the road. So we're going to take a look at example 5.7, which is banking an angle. So example 5.7 for banking an angle, we assume that we have a car with a mass of m, a velocity or tangential speed of v, and a radius of a turn r. So these are all variables. We don't actually have numbers for them. So that means that we're going to be solving using variables only. And we're going to say what banking angle theta is needed for these variables up here. Okay, well, for this car, all right, we'll assume that we've got this angle theta, and here's our car driving right here. All right, for that car, we're going to have normal force up, gravity down, and we're going to assume that we don't need friction. Alright, because we want this to be the safest possible condition. So we set an axis system. Alright, where one of the axis directions points in the direction of our net force, which we want to be a centripetal force. So in the y direction, we've got, alright, here's our normal force. There's our mg. Now we have to place our angle. Our angle belongs right there from similar triangles. And if we do that in the y direction, we've got the y component of normal force, Fn cosine theta, and then we've got mg, and that equals 0 because we're on Earth with regular conditions. And in the x direction, if we assume we don't need friction, the friction doesn't exist, then the only force in the x direction is the x component of the normal force, Fn sine theta, and that will equal ma for circular motion. That will be mv squared over r. So now I've got Fn sine theta equals mv squared over r. If I'm going to solve for this particular angle, then I need to eliminate my unknown force n. For a car of mass m and a velocity v with a radius r, well, I can use this equation to say Fn sine theta equals mg. So that means that Fn equals mg over sine theta. I'm going to go ahead and I'm going to plug that in right there, and I get mg over, oops, sorry, cosine. Mg over cosine theta times sine theta equals mv squared over r. Goodbye m's. And then I see another trigonometric value right here, sine over cosine equals tangent, so dg tangent theta equals v squared over r. Remember, I'm solving for the banking angle, so I need to move the g over, and I get that tangent theta equals gv squared over r. Now that's all well and good, and you can solve for the inverse tangent here, or you can say, well, I've solved for the angle in form of tangent. So now we could say, well, what if we had actual real values for this? What if the velocity were 50 kilometers per hour? And what if the radius were 50 meters? Notice I didn't give you a value for the car mass m. And there's nothing wrong with that, because what happened to that car mass m when we solved this equation? We found out that the mass didn't matter. The mass left the equation, so this will be true for a car of any mass, any vehicle of any mass. So 50 kilometers per hour is equal to 14 meters per second. I did that conversion in my head. Lies. So I can solve for theta now. Tangent theta equals g 9.8 meters per second squared times v squared 14 meters per second squared over r 50 meters. So tangent theta equals 0.40. Take the inverse tangent of that, and theta equals about 22 degrees. So that means that if you would like to travel 50 kilometers per hour around a curve with a radius of 50 meters and not require any friction, so the road could be as slick as ice with absolutely no friction, even though that situation doesn't actually exist, but you would be able to stay on the road and make that curve as long as the angle were 22 degrees. If that's the case, then you will be able to make that turn without any negative consequences. So this gives you an idea of how to apply circular motions to turning in a car, whether there's an angle or a flat road, and how frictions roll and the importance of static friction is in driving.